Let's continue with this topic of as I mentioned to you, that most important difference between the conventional design procedures and the performance-based design procedure is the consideration of the nonlinearity. So if nonlinearity is the main difference, then we should understand what is nonlinearity and how can we include that into our models for analysis. First of all, as I mentioned in the morning, structures are damaged in earthquakes. We know that. So even if we design them well, they are still expected to be damaged. We have seen that we are just saying they should not damage too much. Now, the term too much needs to be qualified. So the structures actually will not behave linearly. And one thing is very clear. If the structure behaves linearly, that means that if suppose I make a model of a small frame, 2 columns, 1 beam, and I apply a load of 1 ton, you do the analysis, you get a displacement of 1 centimeter. You apply 10 tons, you get 10 centimeter. You apply 100 tons, 100 centimeters. Million tons, million centimeters. What does it mean? Can the structure take a deformation of 1 million centimeters? But your analysis will indicate that. So that means there is no check in the elastic analysis on the capacity. Whatever force we apply, you will always get the results. So how do we know these results are not correct anymore? Because at some point in time, those results start to be incorrect because that deflection was not possible. So that means the deflections obtained by the elastic analysis and the corresponding forces cannot be reliable after a certain level. So that means we need the nonlinearity to be considered. Reinforced concrete especially is a highly nonlinear material. Why? First of all, it is many materials together, not just one material. It cracks, it damages, it disintegrates. Then, in that case, using linear analysis is not reliable. So nonlinear analysis, like for example, pushover analysis and time history analysis need to be used. And linearity or the conditions of nonlinearity, actually definition is quite, I would say, restrictive. Linear portion of the structure response is very small and it becomes nonlinear very quickly. We will see in a minute. So, which means that we should have the mechanism to include the nonlinearity into the analysis. But let's see, where does it fit in? Starting, okay, you can read this slide. Let me just explain the stuff, important stuff. Let's start with this equation. This equation is our primary structural analysis equation. In fact, the only equation that we need. This is the equilibrium equation of a structure at a given time. It says that the force, external force, is equal to the internal components of the force in terms of mass, acceleration, damping velocity, stress and displacement, and nonlinearity. Nonlinearity is part of the equation. So, which means that we need to be able to evaluate that for this equation to work. And most important part of this equation is K, stiffness and displacement. Of course, damping, also important. We will talk about that. And mass, well, mass is there. You can't do much about it. Of course, you can reduce the mass. But you can control damping and you can control stiffness, which means you can control this equation equilibrium by those factors. So we have to change the orientation from just saying that this is the force and I need to design for this force. We say no, we can control the force by internal adjustments of the structure because we have control over stiffness and damping and nonlinearity. Now, what is stiffness? Stiffness is a accumulation of levels of stiffness that we have in a structure, starting with material stiffness. going to cross-section stiffness, member stiffness, structure stiffness. Material stiffness, if you remember E, modulus of plasticity E, that is an indicator of material stiffness. E is a ratio between stress and strain. But we know that material stress and strain are related by a curve, not a straight line. So that means right from the start, the material is nonlinear because the stress strain curve is nonlinear. There is no single value of E that we use in the programs. What does that mean? It means nothing because E is changing all the time. So when we use E modulus of plasticity analysis, it actually has no meaning because we are just using one arbitrary value at some point, maybe the start point. But after some deformation, that value is not valid anymore. Second is section stiffness. Section stiffness is a multiplication of two parameters, cross-section geometry and the material. If it is just geometry, it is geometry. But cross-section, when you add material, it becomes a cross-section. And because cross-section, the material is nonlinear, and also the cross-section properties are changing due to cracking, it becomes double nonlinear. One nonlinearity coming from the material, second nonlinearity coming from the changing of the properties of the geometry because section is no longer the same after deformation. So it becomes nonlinear. Cross-section stiffness becomes nonlinear. Cross-section stiffness is equal to EI, for example, or EA. Material stiffness multiplied by geometric stiffness. You multiply, you get the cross-section stiffness. Then comes member stiffness. Members can deform. And what is the stiffness of a member? It is the deformation divided by the length. And that is also, length is also changing. So that means the member stiffness is also changing. Member shape is changing. I mean, the length is changing. Shape also is changing. P delta effects are coming in. So you have another level of nonlinearity added. Then you have structural stiffness, which is a summation of many members. But some members are collapsing during deformation. Some are becoming ineffective. So the structure is also nonlinear. So structural stiffness K that we saw in the previous equation is highly nonlinear because 4 levels of nonlinearities have been added: material, cross-section, member, and structure. So that means when we do the nonlinear analysis, all these 4 levels of nonlinearities need to be modeled and to be considered in the analysis. Sometimes we can ignore 1 or 2 of them, but not all of them, right? Depending upon the structure that we have. So now I'm going to concentrate step by step on each type of nonlinearity and see how it can be modeled. And then in the afternoon, our colleagues will show you actually how to do it in the computer program. I will just discuss the concept. They will show you how what data to input for what purpose, so we can link it together. So that brings us back to the analysis procedures. 4 analysis procedures that we can use, and 2 of them are nonlinear, 2 of them are linear. So we are going to now talk about the nonlinear part of the analysis. Linear part you are already familiar with. So we have talked about the structure level, member level, component cross-section level, and material level. Now, if you look at the member behavior, nonlinearity, you will find very interesting linearity behaviors. This is the linear response that we assume, which goes on forever. That means whatever force you apply, it gives you deflection. No matter how high the force is, you will still get the answer. But actual structures, actual members start to deviate from this line some point and then go in different ways, depending upon what type of nonlinearity is happening. For a brittle member, it will just stop and cross here. It will not become nonlinear. So brittle member will collapse when its capacity is reached, break, and finish. There is no nonlinearity. So it has one step, this X mark. So nonlinearity will not start. Second type of nonlinearity is local buckling. So local buckling, steel members, those people who design in steel know that after some, you have to reduce the global stresses and all that stuff because of this one. Because after a short while, the member starts to buckle because of local buckling. Doesn't go this way, doesn't go anywhere. Then material and geometric nonlinearity may take you this side. Material nonlinearity alone will take you this side. Geometric and material will take you this side. And this one, geometric nonlinearity alone, will go that way. So you can see the different nonlinearities follow different paths. But we combine them together, then we have a complex nonlinear response of the structure of the member. So typically, we need to combine material and geometric nonlinearity. So we are talking about this kind of curve. That means it will start well, then slowly the deformation will change at a faster rate, then you'll have a flatter line, then will go down, and somewhere it will stop or fall down. So that kind of behavior we need to model and trace by including all of these, buckling, material, geometric, into that total response. For the total structure, this is the linear response that you normally think. This is the material nonlinearity alone. This is material geometric, and this is the buckling geometric nonlinearity. So local buckling is not part of the total structure. That is a member level thing. Member will buckle, and it will become a geometric nonlinearity for the whole structure. So this way we can see that, okay, we need to include these nonlinearities into our model and analysis. Two things. Modeling nonlinearity and doing nonlinear analysis are two separate things. You can run a nonlinear analysis or a linear model. The program will not stop you, but you will get nothing, right? You can also try to run a linear analysis on a nonlinear model, which again you will get nothing. So the two have got to go together. Nonlinear model should be correct, and nonlinear analysis should correspond to that model. This is another force displacement relationship, because so basically when we talk about nonlinearity, we talk about FD curves, force displacement curves. They may become stress and strain curve, they may be called moment curvature curve, they may be called anything. But basically, in general, we call them FD curves, force displacement curves. That means any type of force or stress with the corresponding displacement or strain. So you can see that if you start from here, initial elastic stiffness, first yielding, then strain hardening, then ultimate strength is reached, ductile limit, strength loss, residual strength. This is the typical scenario in a member. This is what happens if you load it in one direction and keep on loading it until it goes there. This residual strength is something that even if the member has lost all its capacity, it is still there. It hasn't disappeared. So it still has something left, and that is called residual strength. Normally 20% of the maximum strength is still available in most members, even if because they are not completely gone. They're still part of the structure. But however, if you go load up to this one and start to unload, it may come here, and if you load it again, it may go here and different loop. So that means it will not come back to this point anymore. So that means it's not only nonlinear, it is also inelastic. It doesn't return to the origin. It becomes permanently deformed. If you try to unload, it will come back. Zero, load is zero, deformation is still not zero. This hysteretic problem is the key. We can use it to our advantage, or it can be a disadvantage. How can it be advantage? It can be energy dissipation, because we can use this to dissipate energy, absorb energy, seismic energy. Or it can be a disadvantage. It can lead to degradation and different collapse of the member. So we use this information in the right way. These cyclic curves could be of many shapes. This could be cyclic degradation. That means you reduce. Every time you go, strength becomes less until it falls down. It could be cyclic strength gain, that actually it becomes higher. You will wonder how strain hardening in steel can occur. So you can go higher. It could be strength loss. So you can completely go to a level that you cannot reach back. So complete strength loss can occur. And these guidelines there, they define these types of cyclic models as basic cyclic behavior in a nonlinear response. So you can see from here, without deterioration, with stiffness degradation, with cyclic strength degradation, with fracture, with gradual strength degradation, and so on. So they have identified many, but these 6 are primary types of cyclic response that you can expect from a structure during an earthquake. So actual material and actual member may have one of them or 2 of them. So which means that choosing the right degradation or cyclic model is very important in terms of the analysis. And this is one of the limitations these days we have with our tools. And these days we have a nonlinear analysis. One of the primary limitation is that our programs, software that we have, they do not handle this aspect well. They do not have all of these types of degradation built in. So you cannot model it the way you should. So we are limited by the available heuristic models in a program. And that is where some programs are better than the others, because they have better capability to capture this behavior. Normally, the programs which are research oriented, they are generally OpenSeas, for example, or Romoco, or programs like that. They have much better models than commercial programs like SAP or even Perform, which is considered to be the best program for commercial application. They have limited number of static models, and which is really a shortcoming. So the results that we get from them still have that unreliability factor, because we were unable to include the right type of static behavior for the member. Because there are 4 choices, let's say 3 choices, we can only pick one of them, and it may not be the right one. So that's what makes our program or our analysis a little bit less reliable than it should be. So what we normally do is that we also try to plot what is called the backbone curve. Backbone curve is what is on top of this line. If you connect the tips of each of the cycle, that becomes our backbone curve. That becomes our equivalent FD curve that we can use. If we cannot use the full cyclic response, we use equivalent FD curve, which is connecting the tips of the curve. So this is the one that you will obtain if you test it only in one direction, and this is what you will gain when you do the testing with cyclic included. So that means this degradation actually coming from cyclic, monotonic going this way. And if we are able to include this modified backbone curve, that means we have indirectly included our cyclic response into the analysis. And that is what happens in pushover analysis. In pushover analysis, because it is not cyclic, we try to modify the backbone curve of the material to match with the equivalent cyclic response, and that is one of the key shortcomings or simplifications that we need to do in pushover analysis. In time history analysis, we can use the actual curve, but that is also limited. So this problem with the backbone curve or with the proper static loop is one of the key problems at this time that we are facing in terms of the nonlinear analysis accuracy, because this is not that accurate yet, and we have to rely on whatever best estimates we have. But having said that, let's move forward to, so that backbone curve we can simplify to be like this: A, B, C, D, E. This is most commonly used backbone curve for nonlinear analysis. any type of response we can divide into these 5 points, A, B, C, D, E. A to B we consider it to be elastic. We consider this to be the ultimate capacity yielding point. From here to here we consider to be the ductility and strength gain. From here to here is the drop, and this is the residual, and this is the final point. And this helps us to define our nonlinear model input. This becomes our input. So every type of material response, cross-section response, can be converted into equivalent ABCDE curve, and then put this curve as an input to the program. And then after you put that input into the program does not use that elastic curve anymore. It follows your specified curve. And this is where the control in modeling comes in, because this can be generated based on the actual provided reinforcement and confinement and conditions. So each cross-section, each member, each beam can become unique, because each may have different reinforcement and different confinement and different spacing of stirrups, right? That can now come into, reflect into this curve. So once you put this input into the program, then you can do the analysis. This can be modified by other things, for example, with the P delta effects and so on. So this curve can move down further because of the P delta. You can see from here original, without P delta, and with P delta, this will come down because of that. So that means the P delta effects can be included into the hinge properties that we are developing right there, this curve that we are using. So that gives us the opportunity to combine, because we have seen the previous curves, without P delta, without geometric nonlinearity, and material and geometry can be combined, and we can have a modified backbone curve that we can use as an input. I'm not going to present these slides, please read this. This is a comparison, because time is short, between what is the difference between linear and nonlinear problem. Okay? This is just something for you to read. I have spoken about it mostly. Types of nonlinearity, we have material nonlinearity, as I mentioned, I've shown you a little bit, geometric nonlinearity, and then nonlinear boundary conditions. What does it mean, nonlinear boundary conditions? Soil is also a nonlinear material. We often forget about that. Foundation is not a foundation. Foundation means a pile cap or a footing, and then soil below that. Normally in our mind, foundation means a line with few hatches, which means fixed foundation or pinned foundation, and that's what we think. But actually that's not the case. There is no such thing under the column with 4 lines and a horizontal line, right? There is a footing. Below that there is soil, many layers of soil and water and so many things, which are all just as nonlinear as our materials, even more so. So that nonlinearity of the boundary needs to be included. Not only that, if you have a lot of overturning, the foundation can lift off. That means the contact between the footing and the structure can be broken. So that means no contact. That must be modeled. In a normal model, the foundation will pull the structure down. In reality, it cannot pull it down. So you need to, unless it is a tension pile or something, it cannot pull it down. So in that case, we need to model the separation or the lift off of the foundation, and so on. Expansion joints and so many separations, boundary need to be modeled. They are all nonlinear. So that means nonlinearity we can divide into material, geometric, and boundary. Modeling, we have members, truss. For truss member, basically yielding and buckling needs to be modeled. Those are the 2 primary nonlinearities. 3D beam, major direction, flexure, and shear hinging. Normally, we consider shear to be brittle and elastic, but many people create shear hinge also. Because shear does have some ductility, even very small. So some engineers may consider to model that nonlinearity also. Some engineers say, no, I don't want to bother with that. I will consider shear to be brittle, and I will not model it as a nonlinear component. So that there is a level of judgment involved there. Column, PMM interaction and shear hinging. Panel zone, shear yielding. Infill panel, shear failure. Shear wall, PM and shear interaction, which we normally cannot do. I put an exclamation mark in front of that. It is still something that is really lacking in our tools. Another shortcoming right now is that all of our design and analysis tools do not consider interaction between flexural and shear. They consider them to be independent in a shear wall, but they are not. So that's another shortcoming that we all know. That's why we have to normally consider the shear to be elastic, so we can take it out of the equation and only consider the nonlinearity of the bending. But in reality, that's not true. String for foundation modeling and could be nonlinear link. So this is what we can do for a typical structure which is composed of these components. Nonlinear model could be, again, taking from this one. This is an excellent document. The Seismic Design Technical Brief number 4 from NERV. And here they summarize what type of nonlinearity modeling we can do. Basically, concentrated plasticity or distributed plasticity. Those two approaches can be used. Concentrated plasticity means that we assume that all of the nonlinearity is happening at one point only, and the remaining member between those points is elastic. For example, if it's a beam, we say that even though the bending moment is changing gradually, but all the nonlinearity is only happening at the end, and rest of the beam is linear. Not true. The nonlinearity may be extending, but we normally, it is kind of true because once a portion becomes nonlinear, the rest of the member does not exceed the forces, so we can eliminate that process. So concentrated plasticity, plastic hinge, or nonlinear spring hinge or nonlinear link can be used. Both of these provide us the opportunity to model frame members and shear walls and whatever by using hinges and links. Plastic hinge and nonlinear link. These are the two components that you can use in SAP and other programs. Distributed plasticity means that the nonlinearity is happening over a certain length. And we model that length, and then we say, okay, for example, finite length hinges. Here, the hinge is zero length, kind of. Here, finite length. So we specify that the yielding will occur on a certain length, and we model that length. Fiber section, we consider many sections to be nonlinear along the height, and they are all interconnected with each other. So unlike each hinge which is independent, fiber sections are linked to each other, and they are the same location going through the entire member. So their nonlinearity is linked. And then finite element meshes. Nonlinear finite elements. Most common of them is these days that we are using is nonlinear shell element. So you can model the entire wall or a slab to be nonlinear by putting nonlinear shell element. So it is no simplification, no lumping of the nonlinearity, no need of a hinge zone, no need of a fiber model. You could directly use finite element with nonlinear elements to model the structure. Of course, this is relatively new and people are getting used to it, but this can give us much better information than the lumped nonlinear model. So depending upon the software that you have, you can use plastic hinges, you can use nonlinear links, you can use finite length hinges, you can use fiber sections, or you can use finite elements. These are the primary tools that we have. Now this is what I was talking about, the combination of the two types of members together to form a system. We can accept that certain members cannot be allowed to yield. They have limited capacity and they must be prevented from breaking.